Hello, everyone, and thank you for joining today's GIA Knowledge Session, a series of seminars on gemology fueled by our decades of research. I'm Stuart Overland, Managing Editor of Gems and Gemology. And in this session, we'll take a close look at the most recent edition of G&G. Joining me today are two of GIA's finest. First up is Dr. Chunhui Zhou, Senior Manager of Pearl Identification in New York. He'll be followed by Nathan Renfro, Manager of Colored Stone Identification in the Carlsbad Lab. So let's look at the Spring 21 issue of G&G. This issue was released in early June of 21. And on the cover here, you see a scattering of loose natural pearls from the Paspaley collection in Australia. Inside, 100 pages of content, and every issue comes with a fabulous wall chart of Spinel inclusions, which Nathan will be discussing later on. This session will focus on GIA research content, but the issue does contain a very important article by non-GIA authors. Next slide, please. This team from the China University of Geosciences in Wuhan reports on the identification of rosin-filled turquoise, which you see in this bracelet and necklace set. And in this slide, we see pale untreated turquoise on the left. In the center, you've got the rosin-filled turquoise, and on the right is turquoise that's been rosin-filled and polished. The Spring 21 issue also contains the annual Gems and Gemology Challenge. The G&G Challenge is a 25-question multiple-choice quiz based on our feature articles from the past year. You can take the challenge by visiting G&G online or by going to the Gems and Gemology Facebook group. So with that, let's dive into the Pearl content. Here is Dr. Chunhui Zhou.
Thank you, Stuart, and hello, everyone. I'm going to go over the Pearl-related contents in the recent issue of Gems and Gemology. So next slide, please. So the cover article is titled The Internal Structures of Known Pinctada Maxima Pearls, Natural Pearls from Wild Mollusks. This article was authored by GIA staffs. And before I delve into the results of this article, I just want to give you a little bit of background information about the project. In 2013, a group of GIA staffs went on a field trip with the Paspaley Pearl Company in the water of Western Australia near Broome, a place called 80 Mile Beach. And the purpose of the trip for Paspaley was to collect wild Pinctada maxima shells according to the Australian shelling quota. But for GIA staffs, our goal was to look for natural pearls from these wild mollusks. And on the right-hand side, you see the lead author, Atitaya. She was on the ship with the Paspaley divers and the staffs during the whole week. And what she was doing was looking for natural pearls from opened wild Pinctada maxima mollusks. So the next slide, please. So after the entire trip, out of more than 20,000 opened mollusks collected by Paspaley divers, we found 774 natural pearls. This is actually not too bad. If you look at the ratio, it's almost 3.8% higher than most people would think about how often you will find a natural pearl from a wild mollusk. But most of the pearls are small in size. The pearl can range from as small as 0.49 millimeter to the largest one is about 16 millimeter, which you can see it in the center of the picture on the left-hand side. And then the largest pearl is a little bit less than 20 carats. And these group of samples represent a rare known pearl samples for us to study according to the field gemology classification code. They are considered as B-type samples because even though we did not collect these shells by our GIA staffs, we witnessed the entire collection, and also we found these pearls in the mollusk. So these are rare known samples from known location, from known mollusk species. So these are very valuable samples for us to study. Next. So some additional information from the article. So out of all the 774 pearls, we found 217 17 pearls in the mantle area, either the mantle lip or mantle hinge, and 138 pearls were found in the adductor muscle area, which is a little bit unusual because we thought that most of the pearls should be produced in the mantle area, but the pearls found in the adductor muscle were quite small. They are usually seed pearls. There were 15 pearls attached to the shell, but they can easily be removed. So they are still considered as whole pearls, not blister pearls. 400 of them, we couldn't tell where exactly they were formed within the mollusk, because when people open the shell, clean out the meat, sometimes we found the pearl in the bucket. So, but we expect that most of them would be formed in the mantle area. One interesting thing is that we did not find any natural pearl in the gonad region of the mollusk, which is expected, as it is not a place where natural pearls should form. But we knew that for the cultured pearls, people usually insert a bead nucleus in the gonad region. So that's the major difference between a bead cultured pearl and natural pearl formation. Next. Just two pictures showing some interesting examples. Some mollusk may contain more than one pearl. On the left-hand side, we see 3 pearls formed in separate pearl sacs. And on the right-hand side, we saw that 2 pearls were formed or were found in one pearl sac. So these are some of the interesting examples we have found during these samples. Next. So here is the major conclusion after we studied internal structures of these known samples. So the article focused on examining the internal structure of the pearls using X-ray and CT technology. So out of the 774 pearls, the vast majority of them have the tight or minimal growth structures, 80% of them, which is expected for natural pearls, no problem at all. About 9% of them showing organic rich, concentric, and various degree of dark or light gray cores in the center. This is also more or less expected for natural pearls. There are also a small amount of pearls having some unusual or not so straightforward internal structures, like the dense core, 3% of them, void, 5%, linear structures, 1% of them, and some unusual miscellaneous structures, 2% of them. So I'll be going through these categories very quickly, just to give you an overview on what they look like. So next. So here you see the first 2 groups. On the left-hand side, you see this is the minimal growth tight structure. You can only see a few growth arcs within the internal inside of the pearls, which is very straightforward natural pearls. On the right-hand side, we have the concentric growth plus dark core features. These are also quite typical natural structures for these type of pearls. Next. Now we have another 2 groups. On the left-hand side, the dense core group. Dense core means they're the core having a similar density as the outer region of the pearl. These are, most of them are still natural looking to us, but there might be some examples having a borderline type of structure, which I'm going to individually talk about them in the next few slides. So on the right-hand side, we see a more suspicious or more challenging type of structure, which is called void. We knew that void structure can also be found in non-bead cultured pearls, which is also called Keshi pearls. So when we are identifying pearls with void structures, we have to look into a number of things, like the size of the void, the shape of the void, the location of the void, the structure related to the other growth structures in the pearl. So knowing these void structures in how in the wild mollusk natural pearls look like would be very helpful in our identification of unknown pearls in the future. Next. So once again, on the left-hand side, we have the linear structure, another group of challenging type of structures for us to identify. Especially, we knew that linear structure can also be found in many non-bead cultured Keshi pearls. So once again, we have to look at the size of the linear, the shape, and its relation with other growth structures. So I'll be talking one example in a little bit later. On the right-hand side are the unusual type of structures, which means that internally they may have some kind of foreign material or something that's, we don't know what it is, but they are usually more natural looking. Let's go to the next slide and we can see some individual examples. So the article actually pick out a few pearls out to give you a further explanation of the internal structures. These are unusual or challenging ones for us. So please note that vast majority of the pearls showing straightforward natural structures, which as we expected, only a few of them having this kind of challenging structures, which will help us to understand how natural pearls or how some of the natural pearls could have been grown. So on the top row, we have this dense, kind of like a concentric growth with an oval core. And inside of the oval core, there's a linear structure. This type of structure is a little bit suspicious to us. So sometimes we may find this kind of features in the non-bead cultured pearl. So this type of structure would be considered as non-bead, or maybe sometimes we see this kind of things, we may call it undetermined in the lab. On the bottom, we have another type of challenging features, a dense core with a side seed structure. A side seed structure is also sometimes seen in a non-bead cultured pearl. But for this one, it looks slightly better because you have a nice concentric growth around it. And in the small seed, you also see some growth structures. But still, it's a borderline case. Next. Here are the two examples of void structures. The void structure is borderline and it looks a little bit suspicious to us, especially the shape of the void on the second one. So the first one, we see a little bit of growth structure inside of the void. So maybe look a little bit better. And but still, these two void structures, I think from the article, it mentioned that these two pearls were formed in the same pearl sac, which is interesting findings. Next. On the top, you see the linear structure. This linear structure is really not good if we see them in the lab without knowing where it came from. So you have this linear in the center, and this pearl has the multiple growths, like two twin growths coming together. In both sides, you see the linear structures as well. So in this case, this pearl is really difficult to identify as a natural pearl if we see them in the lab. At the bottom, you have a broken apart pearl. In the center, this sort of unusual structures, even though it's unusual, we usually can still call it a natural pearl because these sort of things are not commonly seen in the non-bead cultured pearl. Next. Two more unusual pearls. The center looks some kind of foreign materials. On the top, we don't know exactly what it might be, but it looks like it could be a coral inside of the pearl. On the bottom, we see it might be a small shell in the center. For the second pearl at the bottom, you also see a demarcation around at the outer edge. Sometimes people may suspect that it could be an atypical bead cultured pearl. Atypical means people insert something other than shell bead into the mollusk. But in this case, I don't see it to be an atypical because it's really rare to have some kind of shell looking thing in the center and then you have this atypical material. So it still looks more natural to me. Next. Finally, we have two more unusual structures. On the top, you have a partial growth, partial hollow structures, but still looks more natural to us. At the bottom, a little bit more suspicious. You have elongated center structures with partial hollow and the linear structures in the center. This type of structure is borderline case, and we might be, if we get them in the lab, it might be undetermined to us. But the great part about this study is we have been looking through these examples, known samples, and these information would be very valuable to us in the future for identifying the natural versus cultured pearls. Next. So this is it for this article, but we are going to write another 2 articles about the internal structures of the Pintada Maxima pearls. We're hoping that having 3 articles focusing on internal structure of the known Pintada Maxima pearls, whether it's in the natural wild shells or whether it's from the operated farms, it will give us more in-depth information of how pearls have grown over the time and what the difference between natural pearls and cultured pearls. So this is something that we're going to work on in the future. Next. So within the most recent issue of GNG, we also have a short lab note about natural fossil pearls and shell blist from the coast of Florida. Basically, a client submitted the 3 interesting samples shown in the image to us, 2 pearls and 1 shell, and the shell having a little blister at the inside of the shell. These samples look very old, and it was reportedly found under the sediment near the coast of Florida, and they were thought to be fossil pearls. So we studied gemologically, we studied all these samples. The pearl look natural, no problem at all. And the next slide, we see that there are some platelet structure on the surface, and we can even see some iridescence on the surface. The fossil pearls we usually see in the lab are really chalky in appearance, brownish colored, sometimes lacking these features. So we are not very sure at the beginning whether these should be considered as fossil pearls or they may be just really old pearls. So what we did is we tried to we sent some of the powders for the carbon dating, and the results came back as pretty old. Actually, it's older than the instrument can tell, so older than almost 50,000 years. We don't know exactly how old these samples are. Maybe it could be much older than that, but at least we knew that these samples can be considered as fossil pearls. So this is the conclusion of these 3 samples. Next. So that's it for the pearl content for this issue of GNG, but we do have quite a few pearl-related topics in the next issue of GNG, which I'm going to quickly show you, give you a preview. We have a featured article about detection of color treatment and optical brightening in Chinese freshwater Edison pearls. The pictures shown here are the samples we studied. Some of the pearls are treated color, some of the pearls are naturally colored. Then we have a beautiful pearl chart or poster within the next issue of GNG, which is give you a detailed information about the pearl classification, the GIA 7 pearl value factors. We have 2 more short pieces, GNI pieces. One is about natural pearls from European freshwater, Russia, Scotland, and Germany. The other piece is about the unique 14-year-old non-bead cultured freshwater pearls from Lake Biwa, Japan. So that's what's going to happen, and you will see them in the next issue of GNG. All right, so that's it for the pearl part, and I'm going to pass to Nathan right now.
All right, thanks, Chunhui. Okay, we're on to colored stones and diamonds for this issue of GNG. So I'll run through all the content that you can check out in more detail in the current issue. One of the main articles that we have here is how to calculate color from spectra of uniaxial gemstones by former GIA intern Che Shin and some colleagues there. And basically they measured or developed a way to calculate color by using transmission spectra instead of absorption spectra, and are able to recombine the measured polarized spectra to predict the color that you'll get in a gemstone. Here's one of the main samples that they used, which was a corundum wafer. So it's carefully oriented so that you can collect unmixed, polarized, ordinary and extraordinary ray spectra. So ordinary rays on the left and extraordinary ray colors on the right. And when you combine those 2 spectra, you get an unpolarized spectra. And so to deconstruct the spectra, you have to measure the polarized spectra, and then you can add using transmittance, you can add those two components together to produce the unpolarized spectra. So here's the figure that shows the unpolarized spectra and the component parts, the O ray and the E ray, and the green trace represents when they are when those two components are added together, you have the unpolarized version, and that unpolarized spectra, that's representative of what your eye would see in a face-up stone, which is the mixture of the E and the O ray. So one of the problems that was encountered by the authors is that when they estimated the unpolarized spectra from the measured absorption spectrum, the estimation and the measured spectra did not agree with each other, and so they determined that the error was in the method of using absorption as the measuring technique. And so basically they remeasured the spectra in transmittance and added the spectra together in transmittance, and then were able to convert it to absorption and to eliminate this error. This is one of their diagrams to illustrate how when light travels through a uniaxial crystal that's unpolarized, it becomes polarized, and then you have, when it's perpendicular to the optic axis, you have half of the O ray and half of the E ray produced. So this is how they were able to measure the polarized spectra when the light's at entering the sample perpendicular to the optic axis. And so from this shows how the corrected estimated unpolarized spectra matched the measured spectra better once they used the transmitted spectra method. So they fixed the error there. And they also developed a formula to measure the component portions of the ordinary and extraordinary ray as the light travels through the mineral crystal at different angles. And so if you're not perpendicular to the optic axis, the ordinary ray and the extraordinary ray will have different relative component strengths. And so they developed this formula to be able to measure each contribution of the ordinary ray and the extraordinary ray, and that way they can predict the face-up color of the known sample, as long as they have the polarized spectra measured and they have the angle that the light entered the crystal relative to the optic axis, as long as that's known. And this just shows that the theoretical measurements match the estimated measurements for various angles. So this was at 0 degrees, 30 degrees, 45, and 60 degrees, and all of the spectra matched quite well to the predicted spectra. Okay, and then onto as Stuart mentioned before, we have a chart in this issue. It's the micro features of Spinel. So this is continued along with our chart series. So far we've done ruby, sapphire, emerald, diamond, opal, and now this is Spinel. And so these charts are basically intended to give the audience sort of a broad overview of the types of inclusions that you could encounter in a gemstone. And so on the left side of the chart, we have a few examples of synthetics or treated features that you might see. Since there's not a lot of treatments in Spinel, there's, fracture filling and maybe cavity filling, that's about it. And then we have examples of flux Spinel and flame fusion Spinel here. And then in the center portion, we have the vast majority of the photomicrographs are inclusions that you might observe in natural Spinel. And unique to this chart compared to the charts that we've done in the past is we also had a few photomicrographs of Spinel as an inclusion in other gemstones. And so you have Spinel in garnet, Spinel in sapphire, Spinel in ruby, Spinel in peridot. So Spinel is a little bit unique in that way. And so each issue of each copy of the current issue G&G will have one of these fold out charts tucked in the back. And so you can hang those up on your wall, kind of colorful. And so you can see there's, you can add this to your chart collection. And these are some examples of of the types of photomicrographs. This is a cluster of negative crystals in a spinel. This is a lazurite inclusion in a spinel. And these are spinel inclusions in a sapphire. So those are the types of photos that you're going to see. Here's the larval shaped gas bubbles in a flame fusion spinel. Okay, and then on to the lab notes. So this lab note was quite strange. Well, the stone itself was quite strange in that this is a cabochon diamond, and cabochon diamonds are almost never seen because of the difficulty in polishing diamonds into this sort of dome shape. It's much easier to facet a diamond, which is what you would typically see. But this diamond had a dense amount of these sort of light scattering pinpoints that are oriented crystallographically with the host diamond. And so by cutting the stone into cabochon, or the pair of stones rather, these were each a little over 11 carats. And because of the inclusions, you actually have an asteroided diamond. So you have this 4-rayed star visible in these diamond cabochons, which is quite interesting. It's quite a novelty stone for sure. And it was also determined that this pair of stones was cut from the same rough as probably from Zimbabwe. And so the diamond view image showed similar features on both the top of the stone and the base. And so you can see that this was most likely sliced from a single crystal, where the crystal was cut in half and each of the halves was polished into this cabochon. Another interesting note is there was a pair of bicolor diamond crystals that came through the laboratory. Bicolor diamond crystals are pretty uncommon, and so to have a pair of bicolor crystals was quite unique. And so in one of the crystals, you have a very strong pink coloration, and in the other adjoining crystal of each of these two pairs, the crystals were colorless. You can see clearly the boundary between the two crystals. The crystal on the left is very pink, and the crystal on the right is essentially colorless. And in one of the crystals, you can see that there are these strong pink graining lines resulting from significant strain that the diamond would have undergone while it was in the ground. However, that pink graining does not continue on to the other diamond crystal. So that suggests that the pink diamond crystal underwent some strain, and then the second adjoining crystal was overgrown or grown attached to the crystal at a later time. And so it was not subjected to the same kind of strain. There's also a lab note on 4 CBD diamonds that had prominent growth planes. And these CBD diamonds were also HPHT processed. And what you see in the diamonds are these sort of concentric rings, or this sort of bullseye effect. And this is a result of the sort of layered growth from the CBD process. And at the stages of the growth, the various layers, you have sort of some non-diamond carbon that sort of decorate the various layers, which make it visible face up. And here are some photomicrographs showing the sort of more obvious layer in the CBD growth. And so these stones were determined there was no assembly plane or anything that was visible. So this seems to be consistent with just multiple stages of growth in the CBD process rather than an assembled diamond. So this is sort of some unique CBD grown HPHT processed synthetics. We also recently saw in the lab a rather rare faceted Tremolite that's the variety Hexagonite. Hexagonite is colored by manganese, and it's sort of this vibrant purplish pink, pinkish purple kind of color. This particular stone was reportedly from the type locality in New York in the Balmont zinc mines. The stone was faceted by Bill Vance. It's quite a unique collector stone, but Tremolite has some very easy cleavage planes, and so it's quite hard to cut this material, but you can still see some fractures from or some cleavages rather, in the stone. But this stone was a little over 3 carats, so quite large for this material. Really a unique collector stone. Also in the lab notes, there was Cat's Eye Opal that was written up by our Tokyo staff. Cat's Eye Opals, they have been previously reported, but they're certainly uncommon. And so here you can see this series of images shows the cat's eye effect sort of rolling across the dome of the cabochon as the light sources move from left to right. And up close in this photomicrograph, we see that the source of the cat's eye is a result of this sort of uniform brushstroke pattern in the play of color. And that brushstroke pattern, when the stone is cut into a cabochon, much like you get cat's eye effect from needle-like inclusions in, say, chrysoberyl or tiger's eye that produce chatoyancy, the brushstroke pattern is so uniform in this case that you have the similar cat's eye effect because of the cabochon cutting. In the Carlsbad laboratory, we were able to examine this sort of unique type of green opal, and it was unique because it displayed some rather prominent evanescence. And so if you look kind of carefully, you see this sort of glittery effect over this piece of rough. Unfortunately, it wasn't cut into a finished stone, but it was still quite interesting. And in the microscope, we see that the source of the evanescence were all these little metallic inclusions of pyrite that gave it sort of this glittery evanescence. And so pyrite's iron sulfide, which is consistent with the cause of color in this stone. And so the cause of color in this opal was determined to be iron. Also in the lab notes in Carlsbad, we examined a lead glass filled lab grown ruby. Now you may be wondering, why would anybody lead glass fill a lab grown ruby? And I'm not sure that I have the answer to that. And so we were sort of surprised at seeing this observation as well. But internally, the stone had numerous glass-filled fractures. You see trapped flattened gas bubbles in those fractures, and the glass filler lies within those. And there was also some flash effect observed. And in a stone like this, it's pretty difficult to see the curved striae, but using the diamond view fluorescence imaging, we were able to clearly see the curved structure of the flame fusion growth. And so that with the lead glass filling, you know, this stone was most likely quench crackled to induce the fractures and then subsequently filled. Maybe the intention was to make a more natural looking synthetic or lab grown ruby, but it still seems like quite a lot of work to produce such a stone. Also in the Microworld section, we had several interesting entries, one of which was chromite inclusions in emerald. And this emerald was from Brazil. And so you have all these chromite inclusions, which are basically chromium oxide. And one of the main chromophores for emerald is chromium. And so what you see here are these green color concentrations around the chromite grains. And so this is sort of an interesting relationship between the inclusions and the localized green color. We also had quite the novelty diamond that was examined by myself and other GIA authors. And inside just under the table facet of the stone, there was a hydrogen cloud which resembled the profile view of a diamond. So we have this appearance of this stylized appearance of a faceted diamond inside a faceted diamond. So that was quite the interesting inclusion. So this hydrogen cloud, it mimics the cubic crystal structure of the diamond. However, one of the corners was truncated, which is where the appearance of the table facet is. Here's what the stone looked like face up. I think it was a rather small stone, about a ½ carat or so, but quite an interesting cloud in that stone. The PL mapping showed in the cloud area, showed a peak around 700, which was consistent with this hydrogen nickel defect. There was also a map in this the center image, which was the H3 defect distribution, which showed that it was much higher outside of the cloud area. And then the image on the right showed the Raman map of the diamond peak itself. And so that showed that the diamond peak was stronger in the non-cloud area as opposed to the defect area in the cloud. So quite an interesting stone there. Another interesting diamond note for Microworld, written up by one of our Carlsbad staff, Troy Arden, were this rough skin on this diamond had several radiation stains. So this was a green diamond. And so a lot of times a little bit of the skin is left, which shows these natural radiation stains. And the radiation stains were so prominent that when you look at the registered photo pair in reflected light versus transmitted light, so the transmitted light on the left shows the green color of the radiation stains, and the reflected light on the left shows that wherever there's a radiation stain, the surface of the diamond is actually sort of blistered up or expanded due to the radiation damage. And so as the radiation damage is destroying the crystal lattice or kind of creating this disorder in the lattice, it creates this expansion. And so you have this sort of plastic deformation of the surface area of the diamond. This was really quite an interesting example of this phenomenon. Also observed in an interesting opal were these coiled fibrous inclusions. Most likely this opal was from the Sinaloa area of Mexico, where you do have this sort of natural blue body color opal. The body color is typically sort of a grayish blue, but these sort of little coils of these fibrous inclusions were the first that I'd seen in a stone like this. Unfortunately, we weren't able to identify what they were using Raman spectroscopy, so they may have been altered by the opalization process, but they were still quite interesting to observe. We also had a mobile inclusion in an opal for this section of Microworld. And fluid inclusions in general are quite uncommon in opal. But what happened in this case was most likely there was a barite crystal that was trapped within the opal and then subsequently dissolved away, perhaps a crack or something allowed fluids to come in and dissolve that barite inclusion away, leaving this barite shaped void. And as the fluids dissolved it away, the crack was potentially rehealed, trapping some of that fluid inside the void. So now you have a space that's large enough for this bubble to sort of mobilize and move around as you rock and tilt the stone. So quite an interesting inclusion in opal. From our Tokyo lab, or Tokyo staff, there was a Microworld entry that were these large iridescent healed fissures that resembled play of color. And this was in a magmatic sapphire. And so you see nearly parallel to the table, there's this large partially healed fracture. This was a heated stone. And so when you look at the photomicrographs, you see the dark areas, and that's where the sapphire has actually healed back together. But the colorful areas, that's where you have this iridescent interface in this dendritic pattern where the healing has not been completed. And so because of that thin film interface, you get this thin film interference colors, which was quite colorful. And also the heating sort of produced this dendritic pattern, which was rather interesting. For our quarterly crystal by John Cuevila, this issue was about a topaz crystal from, I think it was Pakistan, from the Zhou area. And so there was a rather large phlogopite mica inclusion. The stone also contained albite and manganotantalite, which is consistent with a complex pegmatitic origin. And typically for the spring issue, we generally have a Tucson report. However, because of COVID and things like that, it wasn't so possible to have a virtual or a report on Tucson. So there was a virtual report on the status of the industry for this year. And so basically the report kind of details the things that people have had to do to overcome not being able to meet in person. So a lot of the notes are on how vendors have moved to online sales and had to come up with new and inventive ways to maintain sales despite not being able to meet in person due to COVID. There was, so a few individual notes. Constantine Wild, there's a note about how they've overcome their sales and focused on online sales. And there's a couple of examples of the types of stones that they focused on, including this 20 karat tourmaline, I think this 4 karat and change Imperial Topaz. And they've also focused on color suites. So you have 2 types of aquamarine here, and also tanzanite, which has produced this rather colorful suite. So they focused on that kind of material. There's also a note on Dudley Blough gems and the things that they've focused on, which is, I believe it mentioned that for the first time, Dudley has set up a wholesale website in order to reach customers who aren't able to go to the show since many of the shows have canceled. And so some of his material are these unoiled emeralds, gray spinels, and also some material that's been in the vault for a number of years, which is this blue spodumene, which has been kept in the dark in order to prevent it from fading to kunzite. Eric Bromwart from Columbia Gem House has some of the things that they've done is focus on material that they can get, and there's been some supply shortages with international types of gems, but Montana sapphires have been a strong contender. So Columbia Gem House has a lot of Montana sapphires to offer. So these are also Montana sapphires in the top image. In the bottom image, they've had small stones of fire opal and beryl from Nigeria. Gem Shopping Network has been a big outlet for people. So since they're don't necessarily rely on sales person to person, they've been going strong. And then I think the report also mentioned that even though there's been some supply shortages, a lot of the vendors who would normally sell their goods through cruise ships and things like that, the travel industry, because the travel industry has been shut down, they've been able to funnel some of their material through Gem Shopping Network. So that's been helping with the supply there. Okay, so we have Jeff Hateman from Earth's Treasury. So Earth's Treasury was closed to a small degree, but they were considered an e-commerce business. So their closure didn't last quite as long. But Jeff Hateman had to overcome sort of the challenges presented with all the lockdowns from COVID. He had people working from home and also working with online sales in order to help, keep inventory moving despite not being able to meet in person. Same thing with Josh Hyman from the Philadelphia Jewelry Appraisers. Let's see here. So one of the things that Josh Hyman had noted was that due to the challenges with COVID and basically all the travel being eliminated, he felt like a lot of the discretionary spending had been diverted from travel into jewelry. So business seemed to be doing well in that sense. Rock Creek Sapphire Mining. has been going well, although there's been supply challenges with lots of places from closures, but Rock Creek Sapphire is continuing to be mined by Potentate. Here's a photo of Warren Boyd, Potentate, and their recovery. Also, there was Robert Weldon had an update on the Somewhere in the Rainbow collection. That collection has been was established about a decade ago by private collectors, and is now going to be housed at the Alfie Norville Gem and Mineral Museum in Tucson. So here's the museum. So next time you're in Tucson, be sure to stop by and check out that collection housed there. There's a few examples of the types of material that are in that collection. And for our Gym News notes, this note was authored by some of the Carlsbad GIA lab staff. I also had the good fortune to examine this particular stone. This was quite the viral sensation on Instagram and Facebook not that long ago. This was the Cookie Monster Geode that was that's owned by collector Mike Bowers. And so it's pretty clear to see why this stone looks like the Cookie Monster. The way this stone happened to be cut left these sort of voids as the big bulging eyes of the Cookie Monster, and the cavity inside resembles the Cookie Monster's mouth. And down in this area right here in the microscope, it was interesting that you have this little limonite inclusion, which looked like a cookie crumb. So that was one of the more interesting novelties types of stones that we've seen in quite a while. There was an interesting diamond with a hand-drilled hole, and it was reported to have been drilled 400 years ago, potentially. And so the way they would drill these holes before the invention of lasers is you would use a metal sort of a nail and with some diamond powder on it to try to start the hole. And then once you got the hole started, you could insert a diamond coated wire and draw that wire back and forth in order to enlarge the hole. And so you see in this photo, you see the linear striations from that wire drawing back and forth. Also near the drill hole was this trigon that was left behind. And also we have Bell Sin Ting Wong with the Gramaria Bucciolotti Foundation Award with her jewelry design that features jade, diamonds, sapphire, and an enamel brooch of a Siamese fighting fish. All right, and then on to Stuart for the Q&A session.
All right, thank you very much, Chunhui and Nathan, for that fantastic recap of the spring 21 issue. Let's start with some pearl questions. We'll let Nathan catch his breath. Those ancient fossil pearls from Florida, where were those discovered?
According to the client, it was discovered near the coast of St. Petersburg during dredging, and it's buried under the sediment. So that's as far as we know.
All right, thank you. And jumping across the world over to Australia, where the P Maxima pearls were recovered. More than 770 natural pearls were gathered during that expedition. Do other labs have this? Labs or research institutes? Does anyone else have this kind of reference collection?
Well, well, as far as I know, there are other labs that have been trying to collect natural, especially the lab that's close to the Gulf region, the Donut. They may have done something similar, but I'm not exactly sure if any other labs have this vast collection of natural pearls. I think it's a rare opportunity for us to have these samples, to study them very carefully and then know their internal structures. This is the reference information that we can keep and using it in the future. So as far as I know, there might be other labs having similar activities, but the exact number of pearl they have, I'm not sure.
All right. And so are there any other pearl collection trips happening now or planned for the near future, or is that kind of on hold?
Well, unfortunately, due to the COVID, we do not have any field trip on pearls planned. We did have some prior trips. I think some of the GIA staffs went to Vietnam, looking actually visiting some cultured pearl farms and shell bead nucleus factories. So these kind of activities are constantly happening before the pandemic, and we hope that in the future that we can also restart these kind of expeditions, visiting cultured farms or go to the wild and looking for natural pearls.
Let's all hope so. And one attendee asked, start with a comment. No offense, Nathan, but this attendee says pearl identification seems far more difficult than colored stone or diamond identification. So Chunhui, how long does it take, just walk us through this, how long it takes a gemologist to train and make accurate judgment calls on pearl identification?
Yes, there are quite a lot of things to know and understand about pearl identification. You can start as soon as you joined us. If you are joining us, you can start by learning how to use X-rays and start to identify pearls. But to fully understand the nature of pearls, especially natural pearls versus non-bead cultured pearls, and all different type of species, different type of pearls in the world, that's actually takes a long time. You have to see a lot of examples. You have to read a lot of articles, learning how to use different advanced technology and gemological tests to identify them. People start with identifying bead cultured pearls. It's relatively easy. You put a bead cultured pearl under the X-ray, you instantly see the bead inside. So this is the sort of more straightforward things that you can do. But once you get to the natural pearl part, there are so many different internal structures in the natural pearls. It's just so much more varieties of things that you need to look for, and you should kind of, after seeing all the natural strands, you kind of get to know, okay, what kind of structures we commonly see in natural pearls. And the more you see it, the more confident you are in identifying these pearls in the future. So it takes years. It takes many years sometimes to be able to fully, even for me, I've been here for more than 10 years, 11 years. I've seen many pearls, but sometimes we see a pearl with a very unusual internal structure. So we still have to ask for expert opinions from more senior expert in our institution. Sometimes we have to discuss, we have to debate, we have to make a conclusion at the end. But I'm sure that there are also a lot of challenging issues and difficulties in colored stones, and there's a lot of things to learn in that area as well.
All right, thanks for your insights on that, Sean. We have a great pearl team at GIA. I'm going to jump back to you now, Nathan.
Okay.
So you mentioned about the Spinel chart that there are very few treatments for Spinel. Why is that?
Well, I think one reason is, a lot of Spinel comes out of the ground relatively clean, and it also comes out of the ground with pretty good colors as a general rule. One of the more recent treatments, I suppose, that has come about has been heat treatment with the Mahenge Spinel. And so the heat treatment in that case was intended to remove some of the light scattering particles or improve the clarity, but the trade-off was that the color tended to get worse. So that's not really what you want to have happen. So, I think for the most part, it's just that's the nature that Spinel comes out of the ground, not really requiring as many treatments as other gems like sapphire, for example.
All right, thank you. Going over to Cheshen's article, the question is, why are there only two rays, the O ray and the E ray, formed upon polarization? Can more than two be formed?
So that's a good question. So his article basically focused on uniaxial crystals. And so one of the physical properties of uniaxial minerals is that they split light into two rays, which is the ordinary and the extraordinary ray. Some mineral crystals that are biaxial can form more than two rays, and there'll be things like tanzanite. And in those minerals, you get three polarization directions. So you have alpha, beta, and gamma. And so, but for his article, it was specifically dealing with uniaxial minerals. And in those cases, you only have the two rays, the ordinary ray, the extraordinary ray. And then, of course, when those mix, you have unpolarized, you have mixtures in various ratios of those two rays.
All right. Time is running short, but I have a couple of diamond questions to throw at you. The asterism and natural diamond piece. Before cutting these cabochons, would it be known that the diamonds would display asterism?
That's a great question. With the light scattering particles, it was probably, my guess is that it was speculated that they might, because you would still see all those light scattering particles. But I imagine that until you actually cut it, it would be hard to know if there was enough of a density of those particles to say for sure if it would show asterism or not.
Okay.
That's just my guess, though.
All right. All right. One more. How often are bicolor diamond crystals encountered? And would these likely ever be faceted?
The answer to that is they're very rare. I saw one of these crystals, I think, and I think that's the first bicolored crystal like that that I've seen in the colorless and pink combination. Would they ever be faceted? That's a good question. I would hope not, to be honest, because it's such a unique and rare item. I imagine that there could be some challenges along the interface of those two crystals where, there could be some clarity issues, or maybe even some issues where it may not be as durable where you have those two crystals meeting, but hard to say. But the short answer is I hope they wouldn't be faceted.
All right. Well, that's all the time we have for questions today. So that will wrap up our Q&A. But before we go, I'd like to remind you that every issue of G&G, from the very first to the latest, can be downloaded for free from our website. And that's gia.edu/gems-gemology. You can also subscribe to the print edition and purchase issues and G&G wall charts by going to the GIA Store, and that's store.gia.edu. And if you haven't already, you need to join the G&G Facebook group. It's a vibrant community for all gem lovers, more than 16,000 strong, with a steady stream of fresh content all the time. And finally, please be sure to join us 2 weeks from today on August 19th for the next GIA Knowledge Session. Evan Smith and Aaron Palkey will be discussing minerals discovered and named in the hallowed halls of GIA. So I want to bring back Chunhui and Nathan one last time to say goodbye to everybody. And thank you on behalf of everyone at GIA for joining us today.
Thank you.
Thanks,
Goodbye.
Bye-bye.